All right, so now that we've looked at some quantitative analysis for XRF, let's look at quantitative analysis that happens within the electron microscopy, SEM in particular, for EDS. So there's a lot of similarities between the two, but there are a couple important differences. First, the interaction between the beam and the specimen is different, because it's an electron beam. So that's the first one. Secondly, we can't modify our specimens in the same way. So we can't use the internal standard method. Instead, we need a sample standard, or standard sample, with known quantities to be analyzed. So that's the other difference. So the interaction is different because we're using electrons instead of X-rays, and also we can't modify the specimens like we did with XRF. So because we have to have a standard, an external standard with known quantities, then some of the things we have to keep in mind is that we must measure those two, the standard and the unknown sample, under identical circumstances. Identical conditions. So that means that the electron beam voltage, that means that the takeoff angle, and that again is the specimen to EDS detector angle, and then the dead time. Of the detector. So all of these sort of instrument conditions have to be the same. So this is basically, if you kind of think about it from the point of view of XRF, this was all sort of instrument factors. So since we're using two separate specimens, then we have to keep our instrument the same in both conditions. But again, we still have those matrix effects that were part of the specimen, and so those can still be differences. So the matrix effects, we'll still have to examine those. All right, so the method that we're going to talk about for EDS is known as the ZAF method. The ZAF method. And it's got this funny name because this is an abbreviation, right? So this is this stands for something. So this is the most common. method. And it's named this because we have three different matrix factors. So we've talked about these specimen matrix factors, and we're going to break it down into three sub-factors. So we can calculate, and so I'm just going to go ahead and give you the equations used. So we can look at the concentration of a component I compared to another concentration, and that is equal to this term here, which is the matrix factors. So we have a Z, A, and an F, all with the sub I for that component. And then that's multiplied by the intensity of the ratio of intensities. And so that's equal to Z, A, F, and then multiplied by K. So again, these three represent the various matrix factors for an element I that we're examining. So let me go through all the abbreviations here. So the intensity of I is the intensity of the specimen. When we have the parentheses around it, this means the standard. So it's the element, but it's the element in the standard. And so those have the same meanings throughout. K, this is a lowercase ki, is called the K ratio. And this ideally would represent ratio of composition. Same as intensity, but the matrix factors kind of ruin this. All right, so let me go through the three matrix factors now. So Z, this represents the atomic number difference, or sorry, the atomic number effect. A represents X-ray absorption, and F represents X-ray fluorescence. And we're going to go through these each in a bit more detail. All right, so this ZAF technique is commonly used, and it's used to calculate the matrix effects for each element in a sample. The calculation of these matrix effects is particularly good for what we would refer to as the medium to heavier elements. So let's go through and look at these matrix effects one by one. So again, the atomic number effect, and that is Z. So this accounts for the differences in the generation of characteristic X-rays due to atomic number. So the atomic number change in the matrix. And this itself also has two factors. So the first being electron backscattering. We call this R. So basically, we have some fraction of primary electrons. So this is going to be less than 1, obviously, is backscattered. And does not generate X-rays. So this backscattering is a function of atomic number. So we actually use backscattering in SEM to actually do a certain type of imaging mode, but we'll get to that later. So the main takeaway from this is that elements in the matrix that have higher atomic number will generate fewer characteristic X-rays. Than in its pure state. So if an element is surrounded by another element with a higher atomic number, then it's going to generate less characteristic X-rays because the element around it is backscattering more than it typically would in its pure state. So that's the first part. Secondly, so the second of these factors in the atomic number category is referred to as electron retardation. And this is referred to as S as opposed to R. And its S is for stopping factor. So the stopping factor, this is a result of continuous loss that we have of electron energy due to inelastic scattering. So S is 1 over rho, the density, times the change in energy with distance. So again, S is stopping factor, rho is density, E naught is the accelerating voltage of electrons. And S, lowercase s here, is the distance traveled by electrons. So in this case, when we're talking about the stopping factor, the takeaway here is that as atomic number increases, R, the factor we talked about before, increases, whereas S decreases. So we have these two factors in atomic number effect, and they have countering factors. So that's the atomic number effect Z. All right, so we've covered Z. Let's go to A. So again, A again is absorption, A of I. And this is the same concept as we previously discussed for filtering. So when we talked about X-ray filtering to obtain a pure monochromatic X-ray source, we talked about X-ray absorption, and this is the same theory. So we had, in that case, we had this equation, which you can go back to and find if you need to look at it a little bit more, where X is the path length mu over rho is what's known as the mass absorption coefficient. And then rho is obviously density, as it is in the other equation. So it turns out that this X-ray absorption is the greatest factor. So it contributes the most. X-ray intensity. So let's look at the mass absorption coefficients. For iron and aluminum in a nickel matrix. So the difference here, so if we look at these two numbers, so for iron it's 90, and for aluminum it's 4,837, and this has units of centimeters squared per gram. So iron, aluminum in the nickel matrix, so this is a factor of 50 difference. So this has huge implications for X-ray intensity. So we really need to concentrate on X-ray absorption if you're using the ZAF method. All right. And lastly, going through these matrix effects, we have X-ray fluorescence. And this is again F. So this fluorescence occurs if we have generated X-rays and they're able to cause generation of X-rays from other elements. So this is similar to what we saw for fluorescence in the XRF. So here, if we generate a characteristic X-ray and it's able to then go to another element and also generate an X-ray, that's what this phenomenon is looking at. And so because the generated X-rays are typically going to be lower energy than the primary beam, then they are then going to be less likely to produce another X-ray because they have lower energy. So because we're kind of lessening the energy, it means that there's less of a probability that it's going to do that. So it's really, of the three factors, the least important. It's not to say we can ignore it, but it's just, of the three, this is least important. So there's actually a chance that there may not be any fluorescence. Or concentration may be small. So we won't sort of spend too much time on this, but again, if you look at the X-rays that you would generate in a matrix and you can compare them to the elements in that matrix, then you'll look at the numbers and you'll see that there's not going to be a lot of possibilities because we've already decreased the energy. And so to find another element where it can produce that X-ray and actually do it, the probability goes way down. So that's why this F, or fluorescence factor, isn't super important compared to the other two. All right, so this whole thing that we've talked about, the ZAF method, is similar to that fundamental parameters method in XRF because it requires the computational power, which again is not a problem, right? We can do that. And in a similar way, I haven't shown you any calculations because again, it's this iteration that it does within the program. And it's doing that between the measured intensity, or sorry, the measured and calculated K ratio. And it's doing that until they converge. So this is all done in a program. All right. So just like some of the other methods that we talked about, there are assumptions here. So I want to list just go through them really quickly. So for the ZAF method, the assumptions we make is that the specimen that we have is in the bulk form. So when we say bulk form, we mean that it's, you know, a large piece, you know, like a piece of metal or a cluster of powder, and there's no differences between the surface and the interior. So it's all the same. And we also assume that it's microscopically flat. So there's no roughness to speak of that we have to worry about for the takeoff angle and so forth. So those are the assumptions that we make with this method.